There are three industries: energy, automotive, and IT. The intersection among them is the battery, the energy storage. And that is why the three industries have been putting a lot of effort and money into the energy storage research. As a result of which the battery prices have been falling. The battery prices have been falling 16% on year-to-year basis. I'm connected, Professor Jain?
Yeah, connected, sir.
Okay. The energy prices have been, I think the June does not have this kind of problem. That June gives some kind of indication
Sir.
that I think Google, Meet has to improve that way. If I'm disconnected, I cannot figure out I'm disconnected. So the energy, the battery prices have been falling 16% on year-to-year basis. Today, which is 2020, the cost of the battery is roughly $200 per kilowatt hour, and by 2024, it is supposed to be $100 per kilowatt hour. So every 4 year, the price is going to be half. Now, in this space, there is a particular mention of Elon Musk, and I'm sure that all of you have heard of. He's a South African born Canadian American business man, engineer, innovator, and investor. He has many innovation and research to his credit. He is the CEO and CTO of SpaceX, CEO of product and product architect of Tesla Motors, chairman of Solar City. Now he launched something called Tesla Powerwall, which I'm sure many of you have heard of. Is a battery system for home and business. Now, before the Tesla Powerwall was launched, the best battery on the market was a German battery from Sonnenspicer. Now let's compare the Sonnenspicer battery with the Tesla Powerwall. And I have compared a 10 kilowatt hour Tesla Powerwall with a 10.2 kilowatt hour of Sonnenspicer. Now let's look at the relevant comparison. In terms of the weight, the Tesla Powerwall is lighter, is 260 kg versus 100 kg. In terms of the volume, the Tesla Powerwall has a lower volume. And when it comes to the prices, the Tesla Powerwall is 1/3, less than 1/3 of the Sonnenspicer battery. So it's just one product launch that has slashed the battery prices by 1/3. So there is enough improvement for the battery prices. And catching this idea, Elon Musk has launched a Giza factory. This is the biggest battery factory in the world. By the way, if you look at how the battery industry they work, typically the lithium is mined in Chile, is transported to China. They process the lithium and manufacture the cells. Those cells are transported to many different countries, and they assemble those cells into the battery. Now, in the supply chain, the Elon Musk says that if you create a huge battery factory and cut down the supply chain, then straight away you cut down the prices by 30%. That is 1/3. And catching this idea, he established a largest battery factory in Nevada, which is called Giza factory. It's a 5 billion investment. 40 gigawatt hour of batteries will be produced every year. By the way, today, I mean, not today, I mean, a few years ago, if you summed up the total battery capacity of the world, it is the 50 gigawatt. So, I mean, almost double. He doubled the battery production capacity in the world. And those batteries are 30%, more than 30% cheaper. Now, there is a company called BYD, Build Your Dream. This is a company from China. It is a very wonderful name, Build Your Dream, but that's the name of the company. And they are the automobile manufacturer. Now they are getting into the rechargeable batteries. The battery capacity is going to be as big as Tesla power, the Giza factory of the Tesla. And this factory was supposed to come online by 2020. I don't know what is the situation. I have not followed right now. But once this factory comes up, then the total capacity of the battery in the market is going to be 3 times what it was a few years ago. I mean, if it was X, then Giza factory made it 2X, and BYD factory is going to make it 3X. Now, if the supply chain, the supply and demand, if you go by a straight line method, if the supply becomes 3 times, then the prices has to fall by 1/3 in order to match the demand. So that is how the prices are falling. That was about the Giza factory. There are 12 plus mega factories planned, and they will come online by 2020. They were supposed to come online. Again, I have not followed at the moment because the word is not in the right shape. And in the whole game, you see the Apple, the Foxconn, LG, Samsung is another player. Dyson, by the way, Dyson is there now in the UK company. They manufacture home appliances, and they have some presence in the Indian market as well. Nissan, and many more here you can see. Now, often I get the question, lithium how abundantly lithium is available? Is lithium the scarce resource? In the world estimated today, the total capacity of the lithium, total reserve of the lithium is 13 million tons. Now, if you consider the blue area as 13 million tons, then you just need half a million ton to power the whole world, and which is shown in the red area. So you can yourself see that it is a very tiny fraction of the total reserve of the lithium that is available to humankind, to mankind, and you just need a fraction of the reserve to power the whole world. Now, energy storage business model innovation. One thing which is particularly very interesting to power system engineers. There are 2 companies in the United States today. They are called Green Charge Networks and AICTE. They have a very innovative business model. They go to the individual customer and they say that they will reduce the bill, the electricity bill, by some fraction. You don't have to pay anything. You just have to sign up a 10-year service with us, service contract with us. We will put up the battery free of cost at your location, and we will reduce your electricity bill. And we just need a cut in the savings that you incur. So this is a very innovative model. People don't have to, there is no down payment involved from the customer. They just have to provide the space to keep the battery. And their claim is that they can slash the bill by 10 to 50%. Now the storage disruption at the grid scale. You know, I mean, all of you know that there is very little amount of energy that you can store in the grid today, and that is mainly in the rotor as a flywheel, you know. So all what you produce, that has to be consumed at the same time. So you can think of a supply chain which is just in time. I mean, you produce when you need it, really. At the same instant you produce, and at the same instant you consume. So that's the kind of supply chain the electric grid works today. I will now take a little detour and give you a very brief introduction to the load duration curve. I'm sure if you have studied power system planning, or if you teach power system planning, you must have heard of something called load duration curve. This is a very fancy name, but if you look at the X scale, X axis, then you see the number of hours. And if you look at the Y scale, you see the load. This number of hours, you can think of the hourly electricity requirement, and you order them from, you know, highest to lowest. So that is how you generate this curve. This curve simply means, by the way, the end of this curve is 365 into 24. There are 365 days and 24 hours in a day. So in terms of the number of hours, this should be, the last point should be the 365 into 24. And it simply means that the load on the system that was there for, you know, 365 days, that was this much. Sorry, I'm not able to draw a straight line. That was somewhere this much. So if you take 1000 hours, which is here, it simply means in a year, for 1000 hours, there was a load of 9000 megawatt. So if you look at 500 hours, or maybe a little more, a little less, then you see that on the system there was a load of 1200 megawatt, and that was for a very small period of time in a year. I mean, if you look at the graph here, I mean the table here, then there was a load of 189, 1301 to 1300, 13,001 to 13,189 for 7 hours only in a year. And since the supply has to match the demand, you have to install, the installed capacity has to be a minimum of 13,189 megawatt. So in terms of the utilization, you are using last 189 megawatt just for 7 hours in a year. But you have to have that kind of installed capacity in order to be able to meet the demand. What I'm saying is that if you typically do the analysis is from the previous example, then around 32% of the generation assets, they are utilized for less than 6% of the time in a year. And the rest of the time, that is 94% of the time in a year, they are sitting idle, doing nothing. So it's a huge investment that you have logged in. If you look at the last 189 megawatt, that is used 7 hours, which is 0.08%. But they have to be sitting there doing nothing for rest of the year. 1 gigawatt, 29 hours in a year. So 0.33% of the time in a year you are using. The rest 99.66% of the time, not 66, I think, yeah, you are not using them. The next 1 gigawatt, 120 hours. The point that I am making is that the peaking power is very expensive. And in order to be able to supply the peaking power, the investment you have to make huge investment, and the peaking power, the peakers, they have to sit idle for most of the year doing nothing. Now, the message that is I'm trying to give you is billions of dollars in generating assets used for only few hours in a year, and therefore there is a better way you can manage, and that is by implying the energy storage, and that is the batteries. The peaking power will be obsolete in a few years from now. If you are doing some research in power system planning, or you are looking for peakers, just do a Google search in a Google Scholar, the death of peakers, something, or the peakers will be dying, something like that, and then you will get number of the publications. Yeah. Any questions so far, Professor Jain?
Yeah.
I'm connected. Any questions so far?
Welcome.
Any questions so far?
If anyone having any query or question, please may ask.
Is it slow or fast? How?
No, sir, even pace. Even pace is even, sir.
Okay. So no questions.
No one is asking right now.
Okay. I proceed and then take questions later.
Sure.
No issues. You can
Sure.
collect the questions.
Yeah, sir.
Electric vehicle. By the way, what role will car have in future? The per capita vehicle miles of travel is falling. And this is a trend from the world. People are not driving much. If you look at the black curve, the per capita vehicle miles, that has peaked out. People are not driving much. The newer generation is becoming environmental conscious. It was a time when people had 3 cars, one for going to city center, the other for going to office, the third for going to on a vacation, for a long drive with family, a huge one. So those were the situation some time back in the society. This trend is changing now, and there are many parts in the world where the car sales are declining, and in Australia, car sales are half today than what it used to be 10 years ago in a highly urbanized places. By the way, the Tesla Motors in 2003, it is the company is incorporated in 2003, and they introduced electric car. The Tesla car is more efficient. It's because the electric motor, the efficiency of the electric motor is roughly 95%, and the IC engine is 17 to 20%, which is roughly 5 times more efficient compared to the IC. Cheaper fuel. The Tesla car is cheaper to drive. It's 10 times cheaper. I have the data with me, and if somebody is interested, I can discuss the calculations. But then they have to contact me separately. The Tesla car has fewer moving parts. By the way, it's a good question for those who drive classic car today, the IC engine based car. How many moving parts are there in the car? Is more than 2000. Is a number which is mind boggling. Tesla car has just 18 moving parts. Now, what kind of guarantee you get on your car today is like X kilometer or 1 year, whatever happens first, and this block is repeated 3 times. Am I right, Professor Jain?
Yeah, sir.
Huh?
Yes, sir.
But what kind of guarantee you get on the Tesla car? Is infinite mile, 8 years. So within 8 years, you can go to moon and come back, and you can do it several times. As long as you do it within 8 years, you are still under guarantee. The question is why? What enables Tesla car or any electric car to give you that kind of guarantee? The failure rate of any product is linked to the moving component. If the product has more moving components, then the chances of failure, the failure rate of that product is higher. This is common sense. Since Tesla car has only 18 moving parts, the company can afford to give you that kind of guarantee. You drive infinite miles till 8 years, and you are still under guarantee. Instant torque, 0 to 60 miles per hour, which is 0 to 100 kilometers per hour, in 2.8 seconds. Wireless charging, inductive power transfer technology they are using. By the way, if you have questions, if people have questions, then I can answer many more. I can reveal many more facts about them. The projected cost of electric vehicle with 200-mile range a few years ago was, in 2018, it was roughly 30,000, and most of the products, that is Chevy Volt EV, they were launched for $37,500 US. The Tesla Model 3 unsubsidized cost is $35,000 US. Is a semi-autonomous. It can go up to 215 miles and 0 to 100 kilometer per hour, it can scale, speed to in less than 6 seconds. The Foxconn. Foxconn is the company, they assemble your iPhone in China. They are going to enter into the electric vehicle market, and they are targeting to build electric vehicle for $15,000. Xiaomi, they are going to build a small electric vehicle for $6,400. Now the business model innovation. So what kind of changes you think electric vehicle will bring in the society? First of all, you see huge charging stations today. I'm sorry, not charging stations, the petroleum stations today. So I often used to get questions, and I still get questions. What kind of, the charging today, people have to stand half an hour to an hour in queue to get, petrol filled in their car today in Delhi. I have experienced this kind of, the log jam there. So if the electric vehicle comes, what kind of, the problem will be there when it comes to the charging? By the way, you don't need a fuel station or a charging station. Any home, any house where there is a plug, there is a socket, there is an outlet, that's a charging station. So when you are driving, you just need an app to know where is the next charging station, where is the next home you can go and get your car charged and have a cup of coffee. Based on this concept, this idea, the Renault launched a Airbnb, similar to Airbnb, which is the largest chain of hotel today. L, by the way, this is a Swedish innovation. So L means electricity, BNB. And this simply means that the Renault will supply the charging kit to individual people, individual people like you and me, if they are ready to offer this kind of service. And all what you need is that your address should be registered on an app, and if anybody is driving by, they can stop by your home and have the vehicle charged and pay you. That's it. So you don't need a charging station, the kind of gasoline stations you have today, where the gasoline is stored. The huge infrastructure, you don't need that kind of infrastructure. Now there are many other business models. The Nissan and Tesla, they are offering the free charging stations powered by solar power. Since the marginal cost of the solar electricity is zero, they have set up charging stations along the roads. In United States and also in Norway, they are doing it. Because in Norway, the Tesla car is the most popular car in Norway, where along the road they have the charging stations and they charge your car for free. You stop there, put your car in a charging mode, go and relax, go around, and after half an hour the car is charged. There are many more innovations in this line. The Silicon Valley startup Volta offering free EV charging in exchange for media rights at prime value properties. So if you go to supermarket, you get a free charging, you park your car, you get free parking, free charging, and in lieu of that you have to watch the ads. So those places are full of the advertisements. You watch the ad, and in lieu of which your car will be charged for free. Now, as a power system engineer, you should see the electric vehicle as a power plant on wheels. Nothing more, nothing less. It's a source of energy which is moving, and yeah, it's a power plant on wheel. Now, think about the storage in the grid. I take you to Singapore, and this is pretty interesting, details. The Singapore can be powered for 6 hours on the electric car. Suppose all the cars, I give you the statistics. There are 600,000 electric vehicles, 600,000 cars in Singapore. Now suppose all cars, they become electric vehicle. And on an average, each one of them is powered by a 50 kilowatt hour of battery. Okay. So you have 30 gigawatt of energy storage. And in 2014, Singapore consumed 44,923 gigawatt hour of energy. Okay. Now 30 gigawatt hour of the storage you have, you can power Singapore for 6 hours. A very rough calculation. So think the amount of energy storage you have, distributed energy storage you have in the grid. There is a company called Enel, which is the utility in UK, and Nissan is a car manufacturer. They have come up with a vehicle to grid project in the UK. And under this scheme, Enel and Nissan, they have tied up. The Enel will place a demand for energy on the Nissan, and Nissan knows where your vehicle is parked and at what point you can supply and what is the status of the charge of your vehicle. So how much energy you can supply. And you have, of course, you have to make an agreement with the Nissan, and Nissan can confirm Enel that this much energy Nissan can deliver at this particular location. So Enel and Nissan, they are trading this electricity, and this is happening today. By the way, you will get paid for giving energy to Enel. If you read McKinsey and many other reports and look into the energy future, by 2030, the gasoline, diesel to be obsolete. And by 2025, it will peak out. It will hit the peak, and then the production of the gasoline will decline. Any questions so far?
Sir, can you please elaborate about how electric vehicles are cheaper in terms of fuel than gas?
In terms of the fuel,
Yes, sir.
I think I can, but then I have to go out of this PowerPoint mode. I will come back to this. Please keep this question, and then I will come back.
Okay, sir. Okay.
Okay,
Yeah.
sir. Thank you.
Okay.
Hello, sir.
Any other question?
Hello, sir.
Yeah.
The Middle East country, the producer of oil and gasoline,
Okay.
these are also not supporting this production of electric vehicle and
By the way, the cheapest solar power plant is installed in Abu Dhabi,
Yes, sir.
producing the cheapest. I will come. I have skipped. See, I have very less time, and I knew this kind of problem will come. You know, the connection dropped and those things. And I think I have to finish by 1:10, 1:13, 1:15. How much? You know, I have a deadline 1:10. I don't know how much you can sustain, but you can discuss with me privately the cheapest power. I will come. I have the slides. I will show you later on, but keep this question for the time.
Sir, sir.
Okay. So self-driving cars. You know, it is the Google who came up with the self-driving car. Now, the self-driving car will change everything. And when I say everything, then there are a couple of points that I would like to discuss and many more which I have not listed here. It will make the journey safer because most of the car accidents that take place is due to the negligence of the driver. So that aspect is gone. Less space, parking space, or the road. And you are dealing with the drives. In the electric car, okay. Now, I mean, the braking distance, what is the distance that you need to maintain between the two cars when you drive on the road? You have to maintain a distance such that the half mv square becomes 0. If you brake, okay, then it will take some time to burn that energy, and that energy is converted to heat today. I mean, there is no way you can convert this energy to something else. So conversion of half mv square to heat takes longer time, so you need to maintain longer distance between the two cars today. Now, if you can quickly bring this half mv square to 0, that means you can reduce the distance between the two cars. That means you can put the more car on the same road. And also when you park, you maintain space. You have the door has to open and those things. So the parking space also can be reduced with a self-driving car, which is software driven. The disability is no issues. A blind can drive, a child can drive. Time saving. Today when you drive, if you live in Delhi, I don't know, I live in Bhopal, and I used to, I mean, I think 45 minutes I have to spend one way, 1.5 hours in a day I have to spend in the car to go to office and come back. So that 1.5 hours can be used to do something else. No need to pass the driving test. The better utilization. By the way, typically the US statistics is that you use your private car 4% of the time. Only 4% of the time you use your car. 96% of the time your car is parked in a garage, in your garage, or in your office, or somewhere. Now think about the point of investment. After your house, car is the item that involves a huge investment after your house. So you made huge investment in a product that you use only 4% of the time in your life. Okay, and therefore the investment in a car is a very bad idea. It has a very poor utilization, and this utilization factor can be enhanced, can be raised by the self-driving car. How? When you are not in, when you have reached your home or your office, your car can go and do something else. And this is the reason why Ola and Uber, they are making money, because they have increased the, of course they are not, it's not the self-driving car, they are human driven, but by bringing in more number of bookings using the app, like the mobile app they have increased the utilization factor, and therefore they have reduced the cost of the return, they have increased the cost, the return on the investment, and that is how they are making money. There are, the self-driving trucks will also be on the road. It is being tested. Now, if you go to Singapore, you can take a ride in a self-driving taxi. Is already there. In couple of years back, I think 3-4 years back, it was introduced. There are 33 corporations working on the autonomous vehicle. And by the way, there is one from India, and that's the Tata AICTE. Now, if you have to make an electric vehicle self-driving, what you need? You need the machine vision, and of course the computer and the software. But from the hardware perspective, you need the machine vision. And machine vision is called the LiDAR. Now, if I was giving this presentation in 2012, you would say that this man is crazy. Why? Because the self-driving car which Google introduced in 2012, the cost of that car was $150,000. And out of this cost of the self-driving car, the cost of the LiDAR was $70,000. So the cost of the machine vision was about half of the cost of the self-driving car that Google introduced. Half. Now look at the kind of innovation, the research that has gone into the LiDAR space. In 2013, the cost became $10,000 from $70,000. 2014, $1,000, a 10-time reduction in a year. 2015 to 2016, the cost dropped by a factor of 4, $250. Now, if you look at the journey from 2012 to 2016, do you see my slides? Jan? Professor Jan?
Yes, sir. Yes, sir.
Okay. So now if you see this slide, then from $70,000 to $250 today, maybe a little less. Today is 2020. Now think, I mean, this was covered on the IEEE spectrum, the $250 LiDAR. If you read IEEE spectrum, you must have seen this. Now think about the cost. So what was not possible in 2012? I mean, if the same presentation I would have given in 2012, you would have called me crazy. Forget, this is not going to happen. But in 2016, this is possible because the cost has come down from $70,000 to 250, just $250. Now let's go back to another, improvement in the technology. The world's first 1 teraflop computer in 2000, in year 2000. The space requirement was 150 square meter. The power consumption of this computer was 850 kilowatt. And the cost of this computer was 46 million. In 2000. Now, around 2016, 2017, NVIDIA, you have heard of NVIDIA, and they came up with a Tegra X1, the X1 GPU processor is a 2.3 teraflop processor. The power requirement is 15 watt, just 15 watt, and the cost is $59. This processor has a capability to run deep learning software. It can run computer vision with advanced rendering, and it can be updated over the air. Now, think of a $59 processor and $250 LiDAR. Just think of the two components. Here comes a gentleman called George Hotz. His qualification is he is the first iPhone hacker, and he built a self-driving car in his garage. Now he is selling a kit, which is a hardware plus a software kit that can make any electric vehicle a self-driving car. And he is selling to automakers or directly to the consumers. And he is selling it for 1,000. Just $250 LiDAR and $59 processor. And he has come on Bloomberg television, and he has challenged Google and other automakers like Tesla to come and fight, fight with them on the price war. Now, all the money which Google has invested in the self-driving car, I mean, that's fine. They did it, and they did it for the first time. But just the cost perspective of the technology, the way the technology has improved and reduced the cost, especially the LiDAR and the processor, has enabled any entrepreneur like George Hotz to make any car self-driving and disrupt Google and Tesla. This is going to end in future the end of car ownership. Why would anybody own a car? The mobility on demand. Today, if you need the milk, you go to supermarket and buy the milk. You don't go and buy a cow and you don't keep a cow. The same way, if you have to go from place A to place B, it should be the mobility on demand. So the self-driving technology is going to make the car ride, the ownership of the car redundant, and the asset utilization will go up 10 to 20 times. So from 4%, it can go up to the 80%. By the way, Helsinki is one such country. They have a very ambitious plan to make the car ownership pointless in 10 years. And they are going to reorient the whole traffic in the Helsinki so that it will be unattractive for people to own a car. And that will make the private cars obsolete. Solar disruption. Well, photovoltaic requires no water like traditional energy sources. And if you look at the cost of the solar photovoltaic, in 1970, the cost of the solar photovoltaic was $100 per watt. It has been declining since then. And in 2020, the projected cost is 25 cents per watt. In 2018, the cost was 40 cents per watt. I cannot confirm you how far it has reached because I have not followed. I mean, this is a very disturbing time for the world. So maybe what was going to happen in 2020 may happen in 2021 or 2022. But this is the trend. As a researcher, as an engineer, you should be interested in the trend, where the world is going. It can happen today, it can happen a day before, or it can happen 2 days after. But this is going to happen. Now, what is driving the cost of photovoltaic panel down? The efficiency improvement, which is 3 to 4.5% per year for last 10 years, this has been happening. Economies of scale, production optimization. By the way, most of the solar panels,
Sir, sorry to interrupt you.
they are
Your
being
screen-
manufactured.
Your screen is not visible, sir.
The screen is not visible. Is visible now?
And for me it is visible.
Okay.
What about the others?
Is
Pankaj?
visible now?
Quite visible, sir.
Visible,
Okay.
Yes, sir, it is visible.
Yes, sir. Yes, sir.
It is visible.
Yes, yes, it is visible.
It is visible, sir.
Okay. Okay, good.
That may be the individual's problem.
Okay, no issues. That can happen. Why? There are a couple of things that has happened in the world. Now, if you look at the energy consumption of Iceland, then you will find that over the last 10-15 years, it has gone 3 times up. Why? Because they first utilized the geothermal, and the marginal cost of geothermal is 0. That enabled them to force the world to outsource many of the energy intensive processes to them. So most of the smelting of the aluminum, which is a very energy intensive process, manufacturing of the photovoltaic chips, and the panels, and the manufacturing of the the other semiconductor chips, they are the very energy intensive processes. Now suddenly, as a result of a very cheap energy which is available in the Iceland, the world turned the eye towards them. I mean, the processes, the industry started moving towards Iceland. As a result of which, the renewable energy is producing the renewable energy, the photovoltaic panel, which is the renewable energy. The marginal cost is 0 for the geothermal. The marginal cost is 0 for the solar thermal. And that is why the energy requirement to produce the solar panels, that is falling, and therefore the cost of the solar panel is falling. This is also one of the reasons. Now, if you read the newspaper, not the technical magazines, you will find that solar together with energy storage is cheaper in Australia. Now the rooftop solar suffers another blow as utilities switch tariffs. The utilities have to compete with the rooftop solar power plant. And utilities are reducing the tariff. Why? There is something called grid defection. I mean, this is a word I have never heard of before in my life. I have been a power system engineer for more than 35 years. I have most of my life I have worked in field, dealt with the real engineer. But it's just defection. Grid defection means I can go and tell my grid operator, I don't need connection from you, please disconnect. So I'm defecting from the grid, going somewhere else. And this grid defection has already started in many countries, including Australia. Now the growth of solar photovoltaic may actually accelerate. The current growth is 43% per year. Now, if you keep on growing 43% on year-to-year basis, by 2030 you will hit a mark of 70,000 gigawatt, and that is all the energy you need to power the whole world. Now, I give you a data from the Germany, and that's the projection from, they have done it for 2012 to 2050. If you look at the private investors, the longer curve, the longer bar, which is the black one, 116 billion of euro is to be invested by the private investors. And private investor means you and me, those who have the rooftop solar. So the largest investment in the solar photovoltaic is going to come from the private investor, that is you and me. Now, let's look at the stock exchange, because the stock exchange is the place where they get the nerve. I mean, before the researchers get a nerve, they get it first. Now, have you heard of Warren Buffett? I'm sure yes. He has moved his 20 billion US dollar in the solar business because he sees a huge growth in the solar business and he wants to be a part of the growth. By the way, it was 100 gigawatt by 2022. I do not know what is happening, but this is dead. I can discuss why this is dead, but this is not going to happen. In 2018, I mean, the growth rate was good enough, but after 2018, in this country, the growth rate has fallen, and there is no way you can hit 100 gigawatt by 2022. I don't know what is happening. This is a different story. This is a specific to India, and you know much better than I do. Now, China to install 200 gigawatt solar by 2022. Sorry, 2020. And they are targeting, 200 gigawatt, and yeah, they are on the track, more or less. I have not followed what has happened in the pandemic period, but before that they have been on track. Now the grid parity in 80% of global market in 2018. The Deutsche Bank, if you look at the Deutsche Bank, is a German bank, and they come out with the economic outlook every year. If you look at the 2018 economic outlook, then they have projected that the grid parity, I hope you understand what is meant by the grid parity. 80% of the global market, the grid parity. Grid parity means the cost of electricity from the photovoltaic is equal to or less than the cost of electricity from your grid operator. Now, I said by 2020, the projected cost was $0.25, that is 25 cents a watt. And let's look at what will happen if you hit that cost. If you hit that cost, it's not the grid parity, it's the guard parity. I will explain what I mean by guard parity. By guard parity, I mean the cost of the rooftop solar, the electricity from the rooftop solar will be cheaper than the cost of the transmission. So even if the marginal cost, if you assume that your coal plants are giving you electricity for free, then the cost of bringing that electricity from the coal plant to your power point, so I mean to your home, is more than what the elect cost will be from the rooftop solar. And that is what I have tried to summarize in this curve. The cost of finance means the cost of the interest rate. Typically in the United States, the interest rate is is lower. So if you assume a typical interest rate 3 to 5% or 3 to in this range, the dotted line, just a minute, in this range, then and 7 cents would be the cost of the transmission, roughly. So the cost of the electricity from the photovoltaic is 4 to 5 cents per kilowatt hour. And therefore, even if the cost of finance, the interest rate, they go up to the 10%, the cost of the electricity from your rooftop will be cheaper than the cost of the transmission. And that means the death of the centralized generation. They cannot compete. They will become obsolete. Oil, natural gas, nuclear, coal, they will be dead. Now somebody was asking me about the Middle East. I'm coming back to this question. This is in my presentation. Comparison of LCOE, levelized cost of electricity, oil versus photovoltaic. So few years ago, when I did this study, the cost of the electricity from the photovoltaic was 5.8 cents. This was many years ago. I mean, many years, at least 7-8 years ago. That time, 5.8 cents. And if you have to produce the electricity from the oil, so that the cost of the electricity is 5.8 cents per kilowatt hour, then the cost of the oil should be $10 a barrel. I have simplified my complete argument so that people understand. If the levelized cost of electricity is 5.8 cents per kilowatt hour, and photovoltaic has been giving you the electricity at this rate, and if you want to get the electricity from the oil at that cost, so that the cost of the electricity from the oil is 5.8 cents, then cost of the oil must be $10 a barrel. Okay. Now somebody asked me about the Middle East. In Abu Dhabi in 2016 only, this was the contracted, there was a contract, and the contract was a jaw-dropping cost of 2.42 cents per kilowatt hour. Now let's go back to the previous slide and just make it half. 2.42 cent. If the cost has to be less than half, then the price of the oil, assuming a very linear relationship, which is not linear, has to be less than $5 a barrel. Can you assume the oil will be selling less than $5 a barrel? Of course. I mean, in this pandemic period, the oil on the oil exchange market, that hit a negative cost, but that was precisely another reason, not the actual cost. That was precisely another reason because of which the cost of the oil was negative for few hours. But can you imagine the cost of the oil become $5 or less a barrel? No, it will not be. And that is why the Middle East is worried. They are reorienting their economy. They know it's that sooner or later the relevance of the oil is gone. And once the relevance of the oil is gone, their relevance will be gone. Now, some concluding thoughts. Today it is real. That is how you get your electricity. Now, when it comes to the coal, 70,000 people per year, they are killed in this country because of the pollution due to coal. When it comes to the indoor air pollution and carbon monoxide poisoning due to chulhas, 300,000 Indians die every year. That's the statistics. Cost of air pollution in India, if you estimate, in terms of the dollar, absolute terms, which is $40 billion, 3% of the GDP. And 1 billion plus people are connected to unreliable grid today. Now, coming back to again the coal power plant, is water constraining our energy future? The answer is yes. Coal is sucking China dry. In 1950, China has 50,000 rivers, and today they have only 27,000 rivers. So coal is sucking China dry, which is very clear. Let's come back to this country. Have you heard of Parli? It is near Nagpur, and there is a power plant. By the way, there is a power plant, there is a coal, but there is no water. So you can't run the power plant some of the times in a year. I hope many of you know where Farakka is, because if you travel by train, from mainland India to the northeastern part of India, you have to pass through Farakka. They have NTPC has a power plant there, and I think that was in 2015 or 2016. They have to cut down the production because the water level has gone down. And these are, the instances from India and China. There are many more instances. The coal, the electricity from the coal is a water guzzling business. It requires a lot of water. Now the traditional utilities, if you look at Europe, the traditional utilities are under pressure. their margins are under pressure, their revenues are under pressure, they are going down. The biggest utility in Germany, E.ON is divesting fully from the centralized power plant. Now this is my last slide, and I will end by a quote from this gentleman who was the oil minister of Saudi Arabia in 1970s when the first oil crisis hit. And his statement was, the Stone Age did not end for lack of stone, and the oil age will end long before the world runs out of oil. Okay, this is my last slide. And if you have any, I think there were two questions. One was about the cost, why it is cheaper driving electric vehicle, and the other was about the Middle East. So I have answered the Middle East.
Sir,
Hello.
there is one more question.
Yeah, let me, yes, what is that?
Mr. Ramanand Paul, please ask. He wrote in the chat box, sir, actually.
No, I cannot see the chat book because I'm in the presentation mode. So,
Yeah.
just a minute. I think the Zoom has that kind of. Let me discard the changes which I have made and go back to the chat window. Let me. Yes. Where is the chat window?
No, sir, he is ready to ask. No issue, sir.
Yeah. You just pose the question.
Sir, my question
Yeah.
is how self-driving car change
Yeah.
the existing scenario of transportation system of our country, and is it possible in India?
Yeah,
which,
you just need
which-
somebody to stand on
which is
television. Okay,
Yes, sir. Yes,
8
sir.
o'clock in the evening, and say that from 12 o'clock tonight,
Yes,
your
sir.
car will be invalid. You cannot drive, and you have to buy a electric car. Okay, self-driving electric car. So that is one way. The other way, it will automatically come. The system will orient. The system will adjust. Okay. It looks. I mean, there are self-driving cars in. I mean, the taxis in Singapore and many other places, they are running. By the way, there are. I mean, the regulation has to change,
Yes, sir.
and this is not that easy as it looks, but eventually it will come.
Ramanand, you mute your mic. Ramanand.
There are self-driving cars and these transports running on the college campuses in United States, and even the Google campus they are running it. But there are many more. What will be the future of the insurance industry? Nobody, I mean, no researcher is looking at that, because I speak with researchers from all branches of knowledge like economics and finance and many other people, and nobody is looking at that. Of course, in United States they are looking at this, but in this country nobody is looking at that. And so eventually that will come. The system, I mean, you have a dedicated corridor, the bus corridor and those things. Eventually, you see, I have not, let me go back to my presentation and I show you something called, just a minute, view slide sorter. Self-driving car, okay. Now, the General Motors, they have already launched in a city in United States. I have cut down. By the way, in a survey, do you see my screen?
Yes.
Okay. The Brazil, India, and China. 70% of the Indians, they say that if they get this self-driving car, they will drive it. They are not worried. 60% Chinese and 95% Brazilian. Now, I think makes sense. You see, you look at this. The ride share. The GM have come up with something called ride share lift. Launch first self-driving cars in Austin. The first mainstream deployment of autonomous car vehicles won't be to customers but to a ride share platform. It makes sense for General Motors. The 70% utilization in terms of the time, easier to build a car to work in city limits, and usually in the city limit the speed is less than up to 30 miles per hour, and this opens up the new market for them. By the way, the Tata and many other manufacturers here, they never thought of, they can, they always think in terms of selling the car. They never think of in terms of selling the mobility on demand or something else. So the mindset will change and eventually the system will orient towards that. So it will come. What looks not possible and conventional at the moment, possible and plausible at the moment, eventually that will come. I mean, if 20 years ago I had asked you what will be the telecom, the future of the telecom and the future of the internet, today you have the cheapest internet in the world. I mean, millions of people are buying a smartphone and getting online today in this country. So 20 years ago, 25 years ago, if I had asked you this question, perhaps you would have said no, it will not be possible. Yeah. Coming back to the cost aspect, let me see if I have this cost aspect. Yes, I have. Now, if you drive say 5 years, consider a 5-year period, and you drive 60,000 miles in 5 years, the typical cost of driving a SUV like this is $15,000 over 5 years. Now look at the cost. The EVs are 10 times cheaper to charge, and the cost is 15,065, against 15,000. This Tesla Roadster is 4.6 miles per kilowatt hour. Average retail electricity is 0.12 cent per unit. The cost for 5 years, you can, you have the miles multiplied by the kilowatt hour in the dollars, divided by 4.6 miles per kilowatt hour, and which is roughly $1,565, dollar. So very straightforward calculation. You get it? Professor Jain?
Yes,
There
sir.
was
Yes,
a
sir.
question.
Yes,
There
sir.
was a question, yeah.
Yes, sir.
So you
Thing
can
will
do
be
it in
changed,
rupees.
thing will be
Huh?
changed. Yes, sir. Okay,
You
sir.
can
Yes,
you
I
can do it
understand, sir.
you can do it in rupees. Yeah.
Yes, sir. If we almost 1 lakhs and more, I think more than 1 lakhs.
Well, I have not. I don't think in terms of the rupees. So yeah, you can do it in rupees. Yes.
For EVs, for EVs, sir, ki. And for that is for our conventional cars, it may be 7, 8 or 10 lakhs. Oh, thank you, sir.
Yeah, I don't know. I mean, you can
Thank
work
you,
out
sir.
how much it is. Yeah. So any other question?
Sir, good afternoon.
Yeah.
Sir, regarding lithium-ion batteries, you said so many things, and
Yeah.
regarding battery factory, you said so many things, sir. But I have a question regarding quality test. Sir, before dispatching any battery, we have to do some quality test, right?
Yes, those are specified, and I think I think 12. How much? You see, 50. The typical life of a car is 15 years.
Yes.
Okay, and Tesla tries to optimize the battery for 15 years of lifetime. And assuming one charge and discharge per day and taking some factor, not every day we will be charging and discharging fully. They have come up with, I don't know how much it works out roughly, I exactly don't remember. The number, I think 5,000 or 6,000 they are saying. I mean, you can work out how many days are in a 15 years. And they are putting some factors, 80 to 90%. Okay, you can find on their website, and they
Yes, sir.
guarantee so many so many charge cycle. I mean, the battery life is estimated in terms of the charge cycle, how many full charge and discharge you can do. Okay,
But
so
comparing to
they are guaranteeing that kind of batteries.
yes, sir. Yes, sir. I got your point, sir. But
Okay.
comparing to lithium-ion batteries, hydrogen fuel cells will
No,
be giving
that's not as cost effective as this one.
Oh. But efficiency-wise, maybe.
Why you are worried about the efficiency and efficiency? What is the round trip efficiency of the battery?
Battery efficiency.
You have any idea? Round trip, charge and discharge,
Yes, sir.
more than 90%.
Yes, sir.
You will not get this efficiency with the hydrogen. This stuff.
Thank you, sir. Yes.
I mean, as much as I know, and by the way, I have been away from these topics for last 5 years. I have been doing all kinds of bullshit in administration. Okay, but you will not get this kind of efficiency anywhere except the batteries. So if the efficiency is the point, then batteries win. The problem with the battery is the volume, the energy density, and that is where the gasoline wins today. And as of now, the chemistry is not moving that fast, and people have, the chemical property, the energy storage, the storage aspect, the energy density is challenging. That is where, but in future, whatever chemistry comes, to be successful in the market, they have to be better than the lithium-ion battery.
Yes,
What
sir.
the what is available today. So I don't say the lithium ion battery is something that will continue to remain in charge of, the dominating the energy storage space. But whatever technology comes, that has to be better than this.
Absolutely, sir.
Yeah.
Thank you, sir.
So,
Yeah.
so I think, sir, we can stop here, sir.
Okay.
Okay. So, sir, thank you very much for delivering a very thought-provoking that lecture. I hope all the participants will drive and it will give the new direction for thinking, and they will be benefited from it. And once again, sir, I pay my sincere thanks for accepting our invitation and sparing your valuable time. And I hope when the pandemic situation will be over, you will visit my institute physically also. Sir.
Sure. Professor Jain, I will come to your institute.
Sir.
I was there some time back. I think that was 2016 or 2015. I think 2016 I was there.
Sir, you
I
are
did not.
2016, sir.
Huh?
Sir, I am
Oh,
Champa
you
Nagari
are
from
there,
Champa
Champa.
University. Yes, sir.
Okay. Yes, 2016. Right. Right. Yeah, and I visited the Karbuk area and then crossed the border and went to Bangladesh. So I want to repeat this experience again, and I will come. I did not, go to Bangladesh from, the Agartala. I went
Right.
somewhere, I don't know. I have to look
Chitgaon.
my, the, huh?
Chitgaon side, I think.
No, Karbuk area, Karbuk Tehsil and district are, I don't know. And then there, I knew somebody in BSF. So
Okay.
I stayed there and, in the BSF setup for 2-3 days.
Sir.
So I had a cup of tea with the Bangladesh border guards on the
Okay.
other side. Yeah.
So, sir, still
Okay.
BSF is here. BSF having a frontier here, sir. And
Okay.
earlier I was in BSF establishment. So I am acquainted with so many officers, sir.
Okay.
So that would be helpful, sir. So,
Okay.
with your due permission, I would like to end here, sir.
Okay. If people get questions later on, they can write you and you can send it to me.
Yeah, sir. Sure,
Or you
sir.
can pass my email to them and they can write me directly.
Okay, sir. Okay. Thank you,
Okay.
sir. Thank you very
Okay.
much.
Thank you. Thank you so much. It's nice talking to you guys.
Yeah.
Okay. Bye.
Bye bye. So, dear participants, now time is 1:36, but we have the another session from 2 o'clock because there are two sessions in a row, one from 2 to 3:30, then 3:30 to 5. So I request you all, please, uh, anyhow, you come by 2 o'clock back, right? So we will meet at 2 o'clock. Thank you very much. Yeah, Dr. Chaturvedi.
Yes, sir. Good afternoon.
Good afternoon. Good afternoon. Meanwhile, you can check your that video and with that PPT and other whether it is moving or not.
Yes, can
Yeah,
you hear my voice clearly now?
yeah, clearly, clearly. We can hear.
Okay, my video was also coming good.
Comparatively better.
Okay,
So just check so that there will be no hindrance during the presentation and other things.
okay. So what I will do, I can just I
You
have this
go,
virtual
you
background.
go, you go in the present now
Okay,
and share that there will be entire screen. Share your entire screen. Yeah, so it's coming now. Now you just scroll all these things, whether lights are moving or not. Now moving. It's good.
okay.
Now you can speak little bit whether it is coming.
Yes. Now means
Yeah, yeah.
can you see the screen now?
Yeah. So you just expand it in presentation mode, whether it is full screen, full. You do the full screen.
Yeah. Yes. Is it visible?
Yeah. Very good, very good. It's coming now.
Okay, nice, great.
So can we wait 1-2 minutes more, or we otherwise we can start also because
No,
now there are 24
okay.
candidates. So you just scroll all whether it is you.
That is fine, working fine, no problem.
Yeah.
Mhm. Yes.
So Astos, can you hear me?
Yes, sir.
Okay. So that's why I'm asking everybody available, na?
Yes,
Pankaj,
sir.
Pankaj.
Yes, sir. I'm here.
Okay, very good. So now they are joining. Nandini, can you hear me? Acha, good. Then Tapomai, can you hear me?
Sir, we can hear you, sir.
Yeah, okay. No, I'm just testing whether there is only picture is coming or people are physically available. So
Okay,
both
sir.
the things I'm checking.
Okay, sir.
So good. Now please mute your mic. So right. Now, Professor Saab, we can start now, I think.
Okay, so we can start now.
So
Yes.
just wait. So that I can introduce you, then you can start, right? So shall I start now? Okay.
Yes.
So good afternoon, one and all. Now this is the second half of the fourth day, and we are starting with the second session of today. And we have with us Dr. Pradyumna Chaturvedi. Uh, and Dr. Chaturvedi recently working at VNIT Nagpur as a faculty member in the Department of Electrical Engineering. Dr. Chaturvedi obtained his BTech from the Barkatullah University and MTech from the Rajiv Gandhi Technical University, Bhopal, and PhD from the Maulana Azad National Institute of Technology, Bhopal in year 2010. He published more than 80 papers in various reputed journals and conferences, and he also co-authored one book titled Modeling and Control of Power Electronic Converters, System for Power Quality Improvement from the Elsevier. Dr. Chaturvedi is very active in the outreach activity, and as per his brief, I can say he is conducted more than 6 national and international conferences in the India as well as abroad. He is also a chairperson of IEEE Bombay Section Joint Chapter, and he is very active in various other activities also. And his research interest includes solid state transformer, improved power factor converter, multi-level converters, and fault-tolerant multi-level converter. So this is brief related to Dr. Chaturvedi. Now I request Dr. Chaturvedi to please carry on its session.
Okay, thank you, Professor Arvind Jain. Thank you very much for the introduction. So, my voice is coming clearly?
Yeah, it's coming.
All right, okay. So, good afternoon to all the participants, all the faculty members, students, and all the participants from all over across the India. So just now Arvind sir told me that from across the India, from all states, from all corners, participants are joining this session. So welcome all in this presentation. Expert talk you can say, but I prefer to call this interaction session. So because whatever I am learning, and I am just extending that learning, information, knowledge to other participants in the India, in other institutes. So welcome again. So I will take 1.5, you can say around 75 minutes for this lecture, and 10 to 15 minutes I will reserve for any question answers or interaction in the last. So we will start. So this topic, so we will start this. So this SST or solid state transformer, it is not a new concept. Since last 4 years, I am working on this, and this is, as the name suggests you, solid state transformer. So it will use all the solid state devices like MOSFET, inverter, IGBTs, or diodes, or all semiconductor devices, silicon based, germanium based, or latest you can use that silicon carbide or gallium nitride, or you can say that wide bandgap devices. This SST, I will call from now onwards SST only. I will not take full name of this. So this SST, or you can say this as the PET also, power electronic transformer or smart transformer, or some papers are also on intelligent transformer. All these four names are for the single device or converter, that is SST. So this SST for future renewable energy hub. So this topic I have selected for this just to cope up with the main theme of the FDP going on. So this is my presentation outline. I will first give you the what is the need of this SST and how it evolved, means its evolution from since its inception in 1971 around, and expectations from future electric vehicles and such highly nonlinear loads with RES infrastructure, and it is very non-predictable, you can say. So some is you can predict and something you cannot predict. So the demand prediction is required in implementation of any power electronic battery storage and RES type of infrastructure. So we will see what are the different expectations from future EV with RES support. Then I will just focus on different topologies and configurations of this SST, and then we will have some applications of SST, and then challenges which we are facing to implement this SST in future grid, and then I will just take a brief journey on this DAB, dual active bridge, different topology, control techniques, and whatever work I'm doing here in my research lab. This DAB is very important component of this SST. So now we know that in the traditional grid, this is the generating station. Okay, so I can use this highlighter. Not required. Okay. Okay, so in the traditional grid, this is the generating station, thermal, coal, or nuclear-based, or any other source-based generating stations. Then we have to step up the voltage to very high voltage, EHV or HV, then transmit the power to the local station or substations, and again stepping down the voltage to a lower level required by industries and some residential applications. So we can see that we have to use these huge transformers, all right, and its main function is that it will step up or step down the voltage, and at the same time it will isolate the two circuits from generating to transmission or transmission to distribution side. So isolation and second, stepping up and stepping down the voltage, these are the main task it is performing. But in future, this is the practical solution for self-adaptable or self-healing electrical grid, in which you have to incorporate so many devices like IoT devices, smart communication, smart sensors, and different RES like PV, wind, fuel cell, battery management, also storage, and at the same time you should be able to control the demand response, supply response, everything you have to control automatically using latest IoT technology. So this type of self-adaptable and self-healing electrical grid is not possible with such type of traditional transformers. If you will use these two transformers at low frequency 50 hertz with a very huge and bulky size, then in future applications like electric vehicle and space applications, defense applications, military applications, in those applications, you require two main basic objectives, and those are reliability and second, power density. So power density is the major concern nowadays, because you have to develop the converter or inverter system which will consume very less space and which will give you very high power also. So the power density is the major concern, and such type of transformers is means culprit. These are the devils in for future electric grid. So what is the need of this SST? Now we will come to that point. So this power density and reliability is the major concern, and so we have to reduce the volume of the whole system and increase the watt per inch cubic of the system to be developed. So basically these are the big advantage of this traditional transformer, because it is very highly reliable and robust also, and it will give you more than 99% efficiency, and it is relatively inexpensive as compared to other power electronic converters of the same ratings. But these drawbacks I have taken just to take care of the future need of electric grid, including EV infrastructure, RES, and battery storage management system, and such type of very non-linear loads. So now the need is that you have to interconnect your PV, wind, or other DC sources with the existing grid. You cannot replace the whole existing grid with the new DC grid as the scenario is changing. So to take care of this, there are no DC ports available in this transformer, no DC port available. So where you have to connect this PV and wind or fuel cell battery, you have to ultimately develop some DC port or DC bus, common DC bus at different DC voltage levels. So this is not friendly for a integration of RES and EV and storage. Second is it has no capability of voltage or frequency regulation. That means if you have to control the power flow, voltage and current and frequency as well, then you have to use some additional external equipments or converters which will take care of those requirements. And third one is the large weight to volume, means high power density, means low power density is there. So these are the three main weakness or challenges in traditional transformer, so that we have to develop this SST. Now what it will do and what it will have to perform different duties. in this traditional MVAC bus, what we have to do, the communication based upon this IEC standard and some other standards for smart communication. And second side, this SST will be giving you the flexibility of achieving or implementing low voltage DC bus separately and low voltage AC bus separately. That means you are having a multi-port, multi-voltage system at DC side and AC side also, so that you can connect DC sources and loads at one side and AC load and AC source at one side. So there is no dependency on traditional grid and no dependency on high frequency or low frequency traditional transformer, because this SST will take care of everything: isolation, voltage control, reactive power control, power quality improvement, protection system, everything it will take care, and power flow will be in both directions. This is the major advantage of this SST. So these are the main objectives or main functions which we have to perform in any electrical grid. All right, maybe transmission or maybe distribution, fault management, power management, and energy management. So all these different functions will be taken care of by this single SST, single device. All right, this we will see later on. So the main advantage of SST over traditional transformer are these: high power density, because in this we are using one high frequency transformer for isolation, so that the overall size of the system will be reduced. Around 1/10 of the size will be reduced. So the high power density will be achieved. Second is the voltage regulation. So that means you have to maintain the DC bus voltage and AC bus voltage constant under different load and source transient conditions. So this will take care of all the requirement of voltage regulations at every DC and AC bus automatically using power converters. Third, power factor correction, outage compensation, fault isolation, DC output ports are available, power quality monitoring, control and improvement also. And next, availability of DC links. This will facilitate RES integration into the existing grid. And last one is the easy interface with smart communication and smart grid network. So means whatever else we will require other than this, nothing, I think. So power quality and DC port availability and smart communications, smart grid features, RES integration. So everything is covered in these functions. So these will be taken care of by single SST. And most important thing is that you should be able to flow and control the active and reactive power in both directions, because you are using storage, PV and wind as well, everything. So this is also possible with this SST. Now, as I told you that in SST we have to use one transformer at high frequency, maybe around 100 kilohertz, and sometime it will go up to 1 megahertz also for very low power applications to increase the power density. And it is only due to the development of wide bandgap devices, because traditional silicon based MOSFET IGBT cannot work efficiently at very high frequency of switching. So development of this wide bandgap device like silicon carbide, gallium nitride, and availability of these at high voltage also, it is a major advantage. So now around 20 kV bipolar silicon carbide device is available, which can work at around 10 to 15 kilohertz. And if you will try to reduce the kilobaud rating, then you have to go up to several hundreds of kilohertz of switching frequency, because now everybody knows that SiC and GaN devices are having very low on-state resistance, very low turn on and turn off losses. So switching losses are much reduced in this. So these are different companies which are already manufacturing this type of SiC and GaN based SST also for different ratings. Now we will see in this case why we have to take this and how much old this concept is. Now we have to see. So this SST is nothing but you can see in this picture, in this diagram, this is AC grid. Then we have to use some power electronic converters, rectifier and inverter inside this black box. So rectification and inversion will be inside this box. And this inversion or this inverter will invert this input DC at very high frequency AC. And this high frequency voltage is given to this high frequency transformer. So this voltage at this primary of this HFT will be at around 100 kilohertz or more than that also. And the secondary side of this voltage will be again at the same high frequency signal voltage. So again, we have to rectify this and again invert it to. And if you will require this voltage given to grid, then again invert it. Otherwise, just AND this at this intermediate DC bus. All right. So this concept is not a new concept. We already studied rectifiers, choppers, DC converters, flyback, forward, and then inverters. Everything we have studied. But this is the collection of all those inverters. And while integrating together, this will be having some main problems. Then we have to solve that. And third point is that if you have to use some power converters, in that case, ultimately the power quality will be poor if you are using power converters. So the controlling of these converters will again solve that problem. So power quality will be improved in terms of power factor, efficiency, voltage sag, swell, reactive power compensation, harmonics, everything. This will take care. So this research topic I have selected before 4 years because this MIT research, they have given that this SST is the 10 most emerging technology in future. So this study they revealed in 2010 or before 10 years. So presently I am working on this area only, and this Freedom Center in NCSU Carolina, USA. So what is Bhattacharya and his team? So they are working very hard in this area. So they have developed this SST for some applications like UPS and traction drives. So now again, these are a few advantages which I will not repeat. All right. So this is the main focus. This SST will be applicable, will be beneficial in such applications because if you are using more converters, more switches, then obviously you can say that the reliability will be poor in that case. So more switches, more capacitors, poor reliability in SST. This we have to take care. And the overall system efficiency will be also poor. All right. So, all right, we can improve the efficiency of system just by taking care of ZVS, ZCS, or any other soft switching technique. All right, but reliability is to be studied more and more. Okay, but the main advantage is that you have to use this in applications where you have to go for high power density. All right, so this is the main application area for this. Now we will come to the main structure of the SST. Before during 70s only, 70s, 80s, 1971 around, this was the first topology developed, single stage HVAC to LVAC conversion. All right, so they are using this high frequency link using HFT. So the size will be reduced for this, but there is no DC link here, and this was based upon the cycloconverter type of concept. So the power quality is very, very poor in this case. Size is huge, big size, low power quality, and very less efficiency also. So that and there was no DC port available here. So researchers have developed the second topology, AC, one intermediate DC, and then inverter. In this case, the isolation at high frequency is at source side. All right. And in this third structure, AC, one DC intermediate, and this is the LVAC at second level of the voltage. And isolation is at load end. All right, on back end. Okay. So these two are the different topologies. But the main drawback were again poor power quality. And second thing, there was no flexibility in integrating the different rating of RES in that case. So this fourth one is the most widely used recent SST structure nowadays. This will use different stages. So AC to DC with no isolation. Just you can use any rectifier, simple diode rectifier with some power quality improvement technique only. So improved power quality, active or passive rectifier. I hope means everybody studied power electronic subject, so there's no there's no difficulty in understanding all power electronic converters terms. Then after DC, this is the DC link at 1 voltage level, maybe high voltage or medium voltage or maybe at low voltage. And then this DC again invert to AC inside this block at high frequency, and this high frequency voltage will be given to this HFT, and then this HFT will transmit this power to the secondary side, and again use one rectifier here inside this block only. Then this rectifier will give you DC link voltage at another DC link voltage, and invert this if required. Yeah. If you have to integrate this DC to AC, then only you have to invert again, otherwise stop here and give this DC voltage to all DC loads like battery or EV charging infrastructure. So the beauty of this type of structure is that you have the flexibility. You can end at any point. All right. So this is the most commonly used topology. Now, briefly, I will just give you about the requirement of future EV charging systems. So for this case, we have to use ultimately PV or wind support with the grid power supply to the EV charging infrastructure. So now we know that if you will use this battery or storage with the grid, then the burden on that PV or RES will be less, as we can see from this diagram. All right. Then the challenges in EV technology in India, that is you can say a huge number of challenges it is imposing on EV charging awareness, because we have to develop some or sufficient number of charging infrastructure, charging stations, and there should be very proper monitoring and control of the number of electric vehicles connected to the electric grid or charger. So this prediction is again separate topic of research. Some are doing in that survey study on that topic. So the availability of a sufficient number of charging infrastructure or stations at affordable price, and third one, you should not wait for a long time to charge your vehicle. All right. So these are few, and fourth one is the convenient to you. On the way, you should have some charging of your vehicle on the way, on the go. So all these things are required, but in India it will take means around more than 10 or 15 years to reach to that level. So this is the charging requirements for EV charging. Charger type are available for EV battery, fast and slow or moderate. This I am just giving to you because in SST we have to develop or we have to optimize the voltage level at secondary side of the DC bus or HFT. Okay, how much voltage charger or how much voltage rating of charging station we have to implement. So to take care of this thing, we have to study this type of different charging sockets. So fast socket and slow or moderate charger. So in this case, for 50 kilowatt or 22 kilowatt, 15 kilowatt charger, 10 kilowatt charger. So these are different charger connectors available already. Voltage is different, 200 to 1000, 380 to 480, 72 to 200, and 230 voltage. And the number of charging points or connector guns are 1 1 1 1 1 1 like this, or 3 by 3, 3 of 3, each 3.3 kilowatt each. So these are available charging guns or connectors available. So you can just classify the level of charging, number level 1, level 2, and DC fast charging, 120 volt and up to 16 amperes, 240 volt up to 12 to 80 amperes. Now we will just see this in brief. This level 1 charging. So this level 1 charging, this will give you the charging voltage of 120 volt, and you can charge up to 16 amperes only. Okay, this you can use in your house also, or office buildings. Okay, so there is no additional work required to implement this level 1 charging station. Now level 2 charging, this will be at 240 volt, and this can go up to 80 amperes. So this is, you can say, medium range of the power level or voltage level. All right. So level 2 charging have very smart design. So this is like a plug and play type of thing, and it will also help reducing the energy consumption because you are using this at a high voltage. All right. And this will also offer radio frequency type of identification or smart communication to automatic recovery and restart after ground fault interrupt or main power loss. So this is the major issue in any charging station, which can create a major fault in that. And level 3 charging is a very fast charging, DC fast charging. So if you have to go for level 3 charging, then obviously in SST, you don't have to invert that DC link output at secondary of HFT. So stop at DC level and don't invert that. Don't use any inverter. So DC fast charging at 480 volt DC and up to 125 ampere of the current. So these are the 3 different levels of charging. So just to summarize this basic phenomena. So the charging time, charging station power, energy consumption, and distance traveled. So depending upon this, just classified based upon this. So we can summarize that level 2 charging with this 240 volt 80 ampere charging station will give you, suppose you have to travel for 25 kilometers only in the city only. So this is the power consumption and energy consumption, and this is the charging station power in kilowatt, and the time taken to charge this battery to run for 25 kilometers is 0.75 hours only. So this type of system will give you most optimized charging station or ratings in all aspect. All right. So level 2 charging is most widely used. Now, before going into more about SST, now future need of electric vehicles with RES support. So you cannot isolate EV, RES, grid, and anything. So now it is, these are talking in combinations: PV, wind, RES, PV, or fuel cell, battery, and electric vehicles, and power electronics. Everything is now clubbed. So these are different factors which we have to consider while designing any electric vehicle infrastructure, because it is required and standards are going on to be developed. It is not developed for electric vehicles infrastructure. Okay, so there is no fixed rules for electric vehicles till now in all aspect. It is developing. So battery charging vehicle location also, then public charging stations in numbers, capability, charging time required, everything. Traffic density, EV charging duration also, then surrounding vehicle movement. So nobody wanted to wait for charging or for anything. Nobody want to wait for anything. So people want that they have to go to charging station, and within 2-3 minutes their battery should be charged completely. So you should also take care of the customer's behavior, nature also, है ना? So surrounding customer behavior also, so their nature. So grid to vehicle or vehicle to grid type of thing controlling also required, and smart grid infrastructure and smart communication protocols. So all the features should be taken care by any charging infrastructure required to be developed for future electric vehicle charging infrastructure. So just I have collected a few references only, few work on SST. So in 1970s, this SST concept was used by this McMurray. So this is a well-known name, McMurray inverter. So this McMurray introduced the first SST concept in 1970s in single-stage AC to AC converter. है ना? Poor power quality, poor efficiency, poor power flow controllability, bulky in size, but he has given this concept. And after around 80s, again research has been done to develop this thing using AC to AC buck converter type of concept. In 95, you can see the huge gap in major milestones in SST research. You know? So because there was a very less number of high voltage, high power device available in at that time, and the major thing was the transformer. The major culprit was the transformer at working at 50 hertz, and if you will be able to operate that at high frequency, then the switches connected across the converters, across the HFT bindings, those converters should be able to switch on and off at very high frequency. And that time SCR, GTO, those were only available, which cannot work at very high frequency that time. But now, due to development of wide bandgap devices, we are having second GaN devices. So that's why this area is now accelerating. Okay. So huge gap was there in different milestones of this research. In 95, this PET is again power electronic transformer developed by EPRI lab. 96, K. Harada developed this intelligent transformer. 99, by Sadov, some different converter based upon some multi-level converter based SST topology. Then again in 2008, this is the crucial turning point in the research of SST. 2008, where this Freedom Center, Eaton Center, and then you can say this what is that? This Hart in Kiel University, Germany, ETH Zurich, GS Lai, Kolar, and Joshi, and those people, Fred Blabjerg, those have started means at very large scale for development of this SST. So since last 12 years only, this picked up. All right. So this was the first SST developed in 1970s. It was used for traction drives. In traction drives, we know that this overhead catenary is coming in the engine at a fundamental 50 hertz frequency or 60 hertz, you can say. And this transformer is again used bulky, heavy transformer, rectification and inversion, and then drives control is there in traditional traction drive system. But in this SST based traction drive system, they are using this fundamental voltage frequency from overhead catenary, then AC to AC conversion. So this is a matrix converter, or you can say cycle converter, AC link only. This will only increase or step up the frequency only to some several kilohertz. So this high frequency is given to this transformer. So this is the one concept here in 1970s. So we know that if you will provide or supply or feed a voltage at very high frequency, then obviously the size of the core of the transformer is getting reduced. All right. So this was the basic concept. Okay. So this concept was used for traction drives. Now, so many patents were available in 70s based upon single stage SST concept. So this is having poor power quality and so many drawbacks. Okay. So I will not cover more literatures on traditional SST. This is the modern SST concept used nowadays. Okay. So what it is giving you. Now we know that in SST, this will be having this fourth block diagram, this is, topology, AC to DC, DC to AC, and again AC to DC and DC to AC. So these are the different conversion stages which we have to implement. So see this, you are having one three-phase AC grid, all right, and in each phase you are using some modular type of structure, modular in nature. So this is one module. In this module, you are having one rectifier, one DC link, and having one inverter, one inverter. All right, just a minute. I want to take just.
If you have any query, you can post on the chat box. Anyone?
Rectifier inverter, this will invert at high frequency voltage, give it to this HFT, then again rectification is there, so DC. So AC, DC, DC, AC, AC, DC. So you are having this common DC bus here. So, and in every phase, you have to connect, integrate all such modules. All right, three modules, three modules, three modules in each phase. Now, the beauty of this type of structure is that you are having flexibility in your hand, so that if some fault occurs in any converter or in any device, so that can be replaced or bypassed by the controller, DSP or FPGA very easily, and this will maintain the power supply to the load or grid. All right. You can say output or product of the industry. So this is the beauty of this type of structure, and it will depend upon you how many stacks or modules you have to use per phase, depending upon the rating, current voltage power rating of the system. All right. So this is the phase stack, converter cell, DC-DC converter, and protection at LV and MV side, and everything is inside this. Now we can have one flexibility that every output of this can be given to separate AC also. Otherwise, just connect this in input series, output parallel, or input parallel, output series type of connections, depending upon voltage current requirement of the load side and available rating at source side. Okay, so this is the major advantage of this type of application, and it is not possible without using multi-level converters. Not possible, because otherwise you have to go for very high power rating devices. So I will not go to in more detail about that thing. This slide will give you the feature idea about the size reduction. This I have taken from this IEEE IES magazine in September 2016 for the same power rating for the same application. This is the size reduced with as compared to traditional 50 hertz transformer. It is for 20 kilohertz transformer. If you will increase the frequency of operation of this transformer, then it will still go still or it will further reduce the size of the transformer core. All right. Now we will come to the research type of research contribution from my side. So this is the component of SST. So now it is more clear picture. AC grid, one rectifier. It is not a simple rectifier. It is a improved power quality converter used at this stage, so that this will take care of supply current THD, supply current power factor, and this will also maintain this DC link voltage at constant level. Under different backend or DC or load and conditions, and under all input side power quality problems, sag, soil, and other things. So this is improved power quality converter, having again efficient and high power density converter. Now this DC link is at 1 voltage level, like MVDC, around 10,000 volt DC. Invert this, use 1 HFT, again rectify this, use second DC bus here at LVDC bus, ratings, and if required then invert this to AC, otherwise stop at LVDC. Okay. Now out of these converters, the major component or most important component of this SST is this middle stage. This is the SST basically. DC to DC conversion. So this is the most important stage of this. So this is implemented like this: input DC, output DC, one H bridge common to both sides of the transformer, and this is a HFT working at a high frequency, having a turn ratio 1:10 or 1:1 also sometimes in some applications. Now we have to see how we can control this SST or different component of SST. So to control this SST, these are the 4 objectives which we have to meet. All right. It should be able to provide a seamless power supply to end users with good reliability. All right. This is the major objective, prime objective. It should be able to provide voltage balance control at each DC link. It is a very difficult task to make balanced voltage in such type of applications. Here in such applications which give you so many advantages, but some point you have to take care, because slight mismatch in the voltage at each DC link here or here will create huge problem of power quality, harmonics, and everything, or losses, stress on the device also, everything. So we have to take care of this thing. We have to balance the voltage across each DC link very effectively and accurately also. All right. Then to provide a simplified control scheme, okay, achieving better transient and steady state response also. It is common in all applications. And next main objective is that it should be able to provide active and reactive power flow control in both directions and capable of mitigating the power quality problems. So in the last point, you can see all things covered. You know? So active power control, reactive power control in both directions, power quality problems mitigation. And other than this, power electronic engineers does not have any more expectations from industry. You know? So these are the main, you can say, main expectations coming from industry from power electronic engineers. Now, based upon this discussion till now, we can summarize that these are the major challenges in SST. Okay, So depending upon the huge number of power electronic components, converters. Second, depending upon HFT used inside that, है ना? So we can say that it is less reliable. It is having less conversion efficiency overall as compared to traditional low frequency transformer based grid. System is a little bit complex, and last one is the we have to make it compatible with existing protection system. All right, so these are few major challenges. Out of these, efficiency part you can improve using SiC or GaN devices or ZVS, ZCS or any passive components. Reliability we can improve by reducing the total number of devices in the same converter, like some recent topology of multi-level converters with less device count, which will give you improved power performance. Okay, complexity is not a problem nowadays. You know, we can cope up with this thing. And protection, again another area. So power system person can do for this case also. So these are few companies which are developing this SST: Uniflex, EPRI, G and ABB at different ratings, voltage ratings. All right, and operating frequency of transformer, they only went up to 20 kilohertz, because again problem occurs if you will increase the frequency of the voltage given to the transformer, then the power handling capacity will be reduced. Okay, so you cannot go beyond this for high power ratings. Yeah. So this is the major issue. So based upon these different performance parameters, these companies developed these SSTs. So they achieved 98% also. Okay, this GE for 1 MB only. Power rating is very less, you can see here. If you will go for a high power rating like this 300 kVA, then 92% is there only. Okay, so these are a few challenges, right, in SST, but it is the future of smart grid. So this SST is looking applications in subsea area, marine, traction drives, smart grid and EV. So these are very relevant applications for SST. Now this second part I will focus on development of this main component of SST, that is the dual active bridge. All right. So after having this brief overview of on SST, SST is the future of smart grid or future of electric vehicle charging infrastructure and all such applications. And this DAB is the major component of this SST, DAB. So this picture will give the basic overview of AC grid, then one common AC bus, then rectifier, common DC bus, at 1 voltage, then DAB, dual active bridge, having two converters, DC to AC, then HFT, then AC to DC. Okay, so then second DC bus is available here, then rectifier or inverter. Okay, and all converters should be able to flow the power in both directions. All are bi-directional power converters. Okay, now wind, solar, battery, supercapacitors, fuel cell, any RES can be connected at one common DC bus here through some converters and their proper control. Okay, so all these converters and converters in SST all should be knowing what is happening at other side, so that all are closed loop control. So for a proper energy management system, EMS, all should be having very fast controller like FPGA, all right, to take care of the future smart grid, which will be having smart sensors, smart communication at very fast rate. Okay. And the second DC bus can be connected to different DC loads, traction drives, EV charging, or any domestic loads. And if required, then invert to AC, otherwise stop here. Okay. Now we will come to this DAB part. So this DAB for SST is having this type of structure. This is developed by this Freedom Center in NCSU, Carolina, USA.